Hello everyone. Now that we know what an OpScript does, let's have some fun and write an OpScript to generate a grid of lights. Got a very simple scene here. I'm just going to walk you through it. Got a camera create and a primitive create that's creating a plane. And then I'm just setting the viewer object settings to purple for the plane, so it's a bit easier to see. And then I'm just assigning it a material, just a standard material. Then I've got Gaffer 3, which is creating an area light. And now I've got my grid light here, which is a group node, which is going to be doing our heavy lifting. Here I've already added some user parameters. The first one is the light location. This is pointing to the area light that I've made in my Gaffer 3. And this is the one that we're going to be putting on the grid, and then the number of lights we want in X and Y is specified here. So this is going to make us 5 by 5, so 25 lights. And then I've just made it as a slider, so it's easy to change how many lights you want. And now inside my group node, just going inside by Control Enter, I've got my grid, which is another primitive create node of polyplane. And for the name, I'm using root world geo light grids and then combining that with node name as an expression. The reason for doing this is if I were to copy my light grid now, the node always has to be unique. So this will automatically call it grid 2. And then I would have a unique grid that I can put some lights on. Okay, and then I'm setting my grid to be a wireframe. And I'm setting the visibility of my grid to 0. This means I can use it to put my lights on, but the grid won't actually be sent to the renderer. Then I'll just merge the grid in. And next is the OpScript, where we're going to be doing our code. I've already set the cell statement to point to the user light location on the above node. And at the bottom here, I've set some user parameters. So again, I'm grabbing the user.x from the parent node and the y, and I'm grabbing the grid location by using getParam and giving it grid1.name. I'm also getting the light location as a user parameter and taking the light location and splitting it by the forward slashes and the last value to get the light name. I'll explain why I'm getting the light location and light name at the end of the video. Okay, so let's start by doing some code. First thing I want to do is grab hold of our X and Y values. So we're going to do that by doing interface get op_arg and going to get the user.x and user.y values. This will come in as a attribute and then use the get value to get the value of the attribute. And for the X, I'm going to store it as a local variable called X. And then for Y, I'm going to store it as Z. It's maybe a bit confusing, but the reason why I'm doing that is because technically it is Z. It makes it a little bit easier for my brain when I'm coding it. And I think it makes more sense in the interface to be sort of X and Y rather than X and Z. Okay. Also want to get the light location as a variable. So I'm going to do local light location equals interface.get input location path. So this will grab hold of the current location that we're running on, which would be this location here, root world geo light gaffer area light. Okay, now how can we take our light and create a copy of it? Well, there is a interface command for that, and that is called copy location to child. And then you just give it a name and it will copy location to that child location. Now, what you might have seen here is I've got my area light and it's created a child, and then it's created another one and another one and it just keeps going and going. Now, the reason for this is every time you create a child location in an OpScript, it then runs the same code again on that child. So we've now created an infinite loop of children. How can we avoid this? Well, there is another interface function that we can use called @root. And what this function does is it checks to see if the code is running on the root location, which is the original cell statement match that you put in, not any of the children that are created in your code. So we're just going to change it slightly. And I'm going to use if interface @root, then create my child. So let's run that instead. Okay, now we have our new light with no children. Nobody wants infinite children. Okay. Now we understand that concept. Let's create the lights for our X and Y coordinates. So to do that, we're going to do 2 for loops. One for how many values we've got in X and another one for how many values we've got in Z. So I'm just going to change this code to this. I haven't got the tab. So what this is saying is for I equals 1 to number of lights in X, do. And also on top of that, for J equals 1 to the number of lights in Z, do. So this is going to loop over 5 times 5, which is 25 times. And what I want to do is get a unique name for each of the children. So I'll take the interface.get input name, so the name of our light, and I'm going to concatenate that using ... That's Lua code for concatenation. And I'm going to add an underscore and concatenate with our I value, and then another underscore, and then J. And now I'm going to use that same interface.copy location to child. I'm going to give it this name that we're storing, and let's run that and see what we get. Okay, now we've got something. I've now created 25 copies of our original light. Cool. We're definitely not done. There's so much more to do, but you can see with just a few lines of code, we can generate a lot of lights. Change this to 50 by 50, that kind of thing. Okay, so what do we do next? Now that we've got our lights, we need to place them. So we want to run some code that's going to be on our children. What we can do is, if we're not at root, then we can do something else. So we're going to add an else statement here, and the code inside here is only going to be run on our child lights. So I'm just going to put some code in now and walk you through what that's doing. So first things first is I'm going to get the time using interface.get current time, so what frame we're on. This will be explained later. We're going to get our grid location, so we know where to put our lights, and that is again using the get op arg, and we're going to do user.grid location and get the value of that attribute. The next thing we want to do is get the values of our lights locations, so this like 1 1 1 2 etc. To do that, we're going to take the output name. So now that we're creating these child lights, this is an output. So instead of using get input name, we're going to use get output name, and we're going to split that. This is using pystring.split. So if you're familiar with Python, it's the Python split but in Lua. And what that will give you is a table split by whatever you give it. So in this case, we're giving it underscore. So it'll give you a table of 3 values in this case, where it'd be area light, I, and J. So 1 1 here. So how do we then get our I and J? What we're going to do is take our table of split and we're going to use this hash split, which is how many values do we have in split, and then -1. So we're going to get the last but one value, and that's going to give us our I, and then we're going to use the same thing but just the last value in our table, and that's going to give us J.
The next thing we're going to do is create an identity matrix. An identity matrix is a matrix that has no transformations on it. This allows you to then add your transformations on top.
And then we do imath.m for matrix, and it's going to be 4 by 4, and D for it being a double. And this is where we're going to store the combination of our light matrix and our grid matrix into a total matrix. And then just for some housekeeping, I'm going to delete the material assign and any xform that's being copied in from the original area line. Okay, now we're going to get into some matrix math. Don't be afraid, it's not too bad. Here we go. So just going to expand this out so we can really look at this, because matrix math is a bit crazy. So the first thing we want to do is we want to get all of the xform information from the entire hierarchy of our light. So to do that, we're going to use interface.get global xform group of our light location. Now this is going to give us loads of xform groups all stacked together. We want to turn all of those groups into just one matrix. Now to do that, there's this xform utils.calculate transform matrix at time. This is now why we needed the time. So we're going to take this light xform group attribute and give it time, and this is going to spit out another attribute, but this is just an attribute that contains a 4 by 4 matrix. Okay, so now we've got our attribute, we want to get that table, so we're going to do get nearest sample on our attribute. Now previously we were using get value because all of our attributes only had one value. If your attribute has more than one value, then you need to use get nearest sample. Now you can have attributes with multiple samples. Say for example, if you had points, then the p-value might have more than one sample, so that you can do motion blur. So you'd have your value at the 0 time sample, and then you'd also have it, say for example, at -0.25 and 0.25. For most attributes, all you need to do is get the value at that one sample at 0. So we're just going to give it a get nearest sample of 0, and then that's going to give us our light xform table. Okay, now we're almost there. We need to convert that table into a matrix. So we're going to use that imath again, and imath.m44d, and give it the table, and voila, we have our light matrix. Okay, now from our light matrix, we can then extract out the scale, the shear, rotate, translate, and the light result, just using this extract shrt shirt, which is scale, shear, rotate, and translate. Okay, and then we just use this, and it spits out all of these different variables that we're storing here. Now, the other thing we want to do is we want to take our light matrix and invert it by using inverse. Now, the reason we want to do that is when we created our child light, it would inherit the xform information from the light, because that's how Katana works. You inherit all xforms from your parents. So we want to get that inverse, and then we want to remove that from our matrix and then reapply the rotation and scale only. Okay, so stick with me and we'll walk through that in a little bit. So we want to do the same bunch of steps for the grid. So we're going to do the same thing where we get the xform group, and we're going to then get it into one xform matrix attribute, then turn that into a table, and then turn that into an actual matrix. And then what I'm going to do is from this matrix, I'm going to just extract the scale and shear using extract, scaling, and shear. Okay, so we've got these two matrices. Now we need to do some calculations. Okay, now to do that, first thing we want to do is calculate how much space it should be between each light along the grid. So first thing is to get the scale in X and Z. So we're going to store the scale of X. So we're taking this vector and we're getting the 0 vector, which is X, and storing it in W for width. And we're doing the same for the second value, which is Z. We're going to store that as height. And then what we want to do is we want to calculate the spacing. Now, because our values go from 1 for our I and J, what we want to do is for the spacing, we want to do the scale in X minus 1. The number of lights that we have minus 1, and then divide the width by that. So, you know, we have 5 lights, we're going to divide it by 4, and that's going to be our X spacing. But if X is 1, so if you imagine this is 1, 1 minus 1 is going to be 0. That's going to create 1 divided by 0, which is infinity. So what we want to do is if it's 1, instead we'll just have the X spacing as the width divided by 2, so in the middle. I'm going to do exactly the same with Z. So that's the height divided by the number of lights in Z minus 1. And if that happens to be 1, we're going to do the height divided by 2. Okay. So now we've got our spacing worked out. What we want to do is we want to remove the scale from our grid and then translate it to the position that it will need to be in. So we're going to do grid matrix colon remove scaling and shear. So now it would only have its rotation and translation. And then we're going to translate it. So if you think you've got your grid and the translate's going to be at the center, we're now going to move it by taking the width divided by 2 and the height divided by 2. So that takes it into its corner, and then we're going to move it along by the spacing. So that's what this is going to do. Width divided by 2, take it back by that distance, and then add on the spacing. So if I is 1, that's going to be 0, so it's going to be no movement. So it's going to be at the corner, and then when I is 2, it's going to move it by 1 lot of the spacing. When it's 3, it's going to move 2 lot of the spacing, etc. And the same for Z. Okay, so now we're placing the lights all the way along the grid. The next thing we want to do is apply the light transforms. So as I said before, what we want to do first is remove the original transforms. So we're going to do take the grid matrix and multiply that by the inverse light matrix to remove the light transforms, and then we're going to rotate it by the light rotate, scale it by the light scale. Okay, that's a lot of math. This has not actually changed anything yet because we haven't stored any of these attributes. So we've got our total matrix. We now need to put that onto each of our lights. Now, if we were to just put this on as the matrix, it would work and it would place it how we would want it. But if we were then try and use another gaffer and inherit those lights, we wouldn't get the the transform information because it's not stored in a way that the gaffer would understand. It needs to be as xform interactive with each of the translate, rotate, scale. As if I show you the original light, if we click here, we look at its xform information, it should look something like this. So xform interactive, translate, rotate Z, rotate Y, rotate X, and scale. You can see on the current light, I've rotated it minus 90 in X, so it points down, and we've scaled it in Y by 5, and then Z by 20, just as a long point down. Okay, so what we want to do is we want to have exactly the same as this. So what we're going to do is create a group builder. So let's go back into our code. Group builder is building a group. So you're making a group attribute, and we're going to put that into a variable called GB. And then you just use GB set. So we're going to set the translate, rotate, etc. So for translate, it's pretty simple. We just take the total translate and we turn it into a table, and we store that as a double attribute called translate. For the rotations, it's a little bit trickier. We need to take each of the Z, Y, and X. So rotate 2 for Z, rotate 1 for Y, and rotate X is 0. And then we want to change it from radians to degrees. So we're going to multiply it by 180, divide it by pi. So using this math.pi. And then you also have to set it as kind of like a matrix where you're doing Z is its first value, and then 0, 0, 1, and then Y is 0, 1, 0, and then X is 1, 0, 0. Okay. And then for the scale, it's the same as translate. You're just doing total scale and then to table. Okay, so now we've got our group builder. We want to put that onto the xform interactive. So we're going to do interface.set attribute, and we're going to build this group. So it's going to create each of these attributes under this. Okay. What? Look at that. We've got some lights on our grid. How cool is that? Okay, so if we will go to one of these lights, we will see we have our translate, rotate, and scale. Nice, eh? Each one has a different value as it's moving along. Okay. Now, there is a slight problem with this. So if you have a light that doesn't have that has uniform scale like this one, and then you rotate the grid, let's see what happens. Take my grid, I'm just going to rotate it 30 degrees in Y. Now, what you'll see is our lights are doing a funky thing, and this is the shearing. So we don't want this. We want our lights to line up nicely, but there isn't any shear for xform interactive. We have to do something a little bit strange, but it works. Is we need to apply the shear, but the order of when you apply the shear is before the scale. So we're going to remove the scale that we've just applied, and then apply the shear, and then reapply the scale. Now, we want to do that so that we still have the scale as an interactive that we can then change further down the line with another gaffer. We have to do this kind of like little funky thing, and I'll show you how to do that. So with xform information, we can just keep stacking xform information on top of it. So as well as xform interactive, we can add more, and that's what we're going to do. So we're going to apply xform group scale, and those values are going to be the x inverted and the y inverted and the z inverted. And then we're going to make a matrix by taking the identity matrix and applying the shear using our total shear, and then converting this new matrix into a table. and we're going to store it as a 4 by 4. So a matrix is 16 values in the table, and then we do comma 4, and that says that each of the 16 values is going to be split by 4. Okay, and then we're going to reapply the scale by using another xform group, and we're going to do a total scale to table, and voila, we've now reapplied our scale after shearing. So you can see here it is. Then we've inverted our scale, and then we've applied our shear matrix. We've recreated the scale, and now our lights all line up as they should with no shearing. Okay, so that's something that's sort of a bit of an obscure thing, but I think it's good to know about. You know, it can trip you up if you don't know. So now we've got all of our lights and they're sitting on the grid. Everything is awesome. Well, but still got a couple of little things we need to tidy up. So firstly, our area light, we don't want this to be a light anymore. We want this to be our rig. So we would need to change the type to rig. And then if you look at the attributes under info gaffer, this package is setting it as an area light package. So we'll just change that to a rig package. And we want to remove the material from it because it doesn't need a material anymore, and this material assignment. And the last thing we need to do is every light that you make, it gets added to root world. So if we go to root world and we look here, we have this light list, and currently it just has our area light. What we want to do is take this attribute and copy it for every one of our lights, and then tweak the values. So we're going to change the path to be the path of you know, each of these new area lights, and then we want to remove this because this is no longer going to be a light. So what we want to do is run our code not only on the area light, we want to run it at root world, and we want to rejig a few things. So how can we do that? Well, we're going to add to this root world. So it's important to make sure you have the space here. And now we have it running at our light location, and we're going to add to that root world. Okay, and then we're going to tweak our script a bit. And this is the bit where I said that why we need to have the light location as a parameter here that we can then grab as an attribute, because when we run it at root world, we need to know where that light location is. So our simple little bit of where we're running it at root and we're doing our for loops, we now need to expand out to also change the root world location. So what I'm going to do is just change this bit of code here and walk you through that. And this is the last stage. We're nearly there. Okay. So I'm going to change it to from our light location to being the input location path to the get op arg of light location and get that value. I'm then going to get the light location and use that pi string split again to split it by the forward slashes. And then I'm going to remove the last value of that. So basically removing the area light bit. So you've got root world light gaffer. And then I'm going to rejoin it with underscores. So each of these forward slashes will be an underscore, because at root world, that's what it is. So it's root underscore world instead of root slash world. Okay, oops, sorry. Go back here. And that's what this bit is. So we're going to do a pi string join and join it all back again with underscores. So now we'll have underscore well root underscore world but we don't want an underscore at the front. So we're now going to do a light path sub, and we're going to make it so that it starts from the second point. So it starts from root, so R, and removes the first underscore. Okay, so all that just to change this to being root underscore world underscore light underscore gaffer. Okay, and then what we want to do with this is add in swap out basically the original light name with our new light name. Okay, so we've got our light name from the get oparg, get value, and while we're doing our loops, what we're going to do is we're going to check to see if we are at root world by again using the input location path, and then is it root world? If it is, now we want to change the light list. So the first thing we're going to do is going to copy. So we're going to go to light list, our light path. So and then combine that with an underscore and the original name, and then copy it for the new light name. Okay. And then the next thing would be fixing the paths, and the last thing would be deleting it. So let me just comment these two things out so we can see what this one is doing first of all. So if I refresh my list, you can see we're now copying all of these, but they all have the same path. So we want to fix that path. And then once we fix that path, we want to delete this original one. So that's what those two other lines are doing. So we're now going to set the attribute of the path to be take the original light location and use the pystring.replace to swap it out with from the original name to the new light name. And that is a string attribute. So we're going to wrap it around a string attribute and set that attribute there. Okay, and then just delete the original light from the light list. Okay, the last thing we need to do is just some tidying up, like I said before. So if we're not at root world, so we're running it on the light, then we're going to change the type to rig. So we're going to use a set attribute of type, and it's going to be a string attribute rig. And then we want to change that light package to be a rig package. And we're just going to delete the materials, like I said. Okay, that is it. We are done. We have created this awesome tool. So now you can see it's a rig, and it's got a little rig icon, and we've got all of our lights, and we've fixed root world now. So we no longer have the original one, and each of these have their own paths. Okay. So now if we go back up to our interface, we can change this around, and we can change the number of lights. So now if we see if it goes to 1, it's now in the middle, and we change this to 1, it goes in the middle. So one light in the grid, which would be the most pointless thing, but it works. And you can see, yeah, it's pretty quick and interactive. We can create lots of lights in this grid. We can move it around wherever you want. Let's just do a render just to make sure it works. So, do a live render. I've already set all of these locations to change as I change the lights. So you can see there's our grid of lights. Now, hopefully this will give you some inspiration of some of the things you can do. For example, you could add a light for every point location. So if you're given a point cloud, if that point cloud had normals, you could point the lights using those normals. You could add lights to locators, you could add lights to geometry. If your renderer has light arrays, say for example RenderMan has light arrays, instead of creating children lights, you could just change your original light to a light array, and then give all of those matrix values that you were creating into one giant matrix array, and then place all your lights with that. So it's quite a few different things you can use this for, and this has covered quite a few different areas of what you can do with an OpScript.
You can now take this node and save it as a macro for reuse.
I hope this helps, and have fun coding.